So good evening and welcome to the next installment of the SLAC Public Lectures. So today we're very lucky to have Liz Ryland from the Pulse Institute here at SLAC in Stanford to talk to us. Liz is from Louisiana originally, did her BA at Louisiana, or BS, I guess, at Louisiana Tech. Then from there, she got to the University of Illinois, one of the big places actually for condensed matter physics. She apparently built her own little X-ray laser and did so well that she got to come here and work with the big one that we have here at SLAC. And so she's been a postdoc at the Pulse Institute. She's going to talk to us about looking for trolls under the electron bridge. So we'll find out what that means. Good luck.
All right. Thanks for the introduction, Michael. So as Michael said, we're going to search for trolls under an electron bridge today, and we're going to spend a while figuring out what on earth I'm talking about. So when I gave this practice talk, they wanted more info about me, so I am indeed from Louisiana. Yeah, it's a great place. It's the land of Mardi Gras food and like aggressively hot sunlight and a lot of plants that grow from that. And that's really all that I'm about. I'm from Shreveport, so the northern part of the state, not exactly New Orleans, which is way down there, but I have family in Lafayette, kind of capital of Cajun country, and kind of have been all over the state. And really, there is sunlight everywhere, sunlight and plants that grow big and strong. And the older I get, the more impressed I got by how massive plants can grow and how much they can do deriving energy just from sunlight and soil and water. So as Michael said, after like childhood and high school and stuff, I went to Louisiana Tech University. It's a big engineering school in Louisiana, and I got my degree in chemistry, and I worked at a college radio station. And from doing those two things, I realized that chemistry is cool, and with my undergraduate degree, I really just only got the barest foundation. So I really wanted to know more. And so I applied to graduate school, and I decided to go to the University of Illinois at Urbana-Champaign. As Michael said, it's a very big school. And there I joined the Josh Veroweiss group, where we built this tabletop XUV instrument, which instead of making really high energy X-rays in about a mile, we made really soft energy X-rays in about 6 feet inside our own lab. And we got to kind of build that all from scratch. It was really cool. And I used that to really start studying molecules on a fundamental level, really tracking the electron movement at the speed that they actually move at. From there, I went to the US Naval Research Lab for a postdoc. I kind of expanded into IR spectroscopy, and that's where I spent the lost plague year of 2020. And then from there, I moved on to SLAC. COVID, not a great time for anyone. So I moved on to SLAC, and even though I had been working in IR spectroscopy, I wanted to expand my horizons. I really like X-rays and all of the different things you can do when you're using those as your primary instrument. So at SLAC, I joined Kelly Gaffney and Amir Cardonis-Han in the solution phase chemistry group of the Stanford Pulse Institute of the SLAC National Accelerator Lab. Really lots of titles. What that means is that we are based at SLAC, and we're really an end user for these giant instruments. So we're not part of making the X-rays, but we're part of using them to answer fundamental scientific questions. So getting into the bulk of the talk, why do we even want to study photochemistry? Is it because there's a massive ball of energy in the sky that's glowing on us constantly? Pretty much. So the sun is really powerful. So the sun is really powerful. It's constantly doing fusion. So it's taking two hydrogens, smashing them into a helium atom and releasing tons and tons of energy. As I have up there, it fuses over 600 million tons of hydrogen per second and releases massive amounts of energy, almost 4 times 10 to the 26 watts per day. That's almost a trillion times a trillion times a trillion of watts of energy. Compared to what actually reaches Earth, because that's emitting in all directions from this sphere in the sky, it's crossing 93 million miles to get to the Earth's surface. And at the Earth's surface, you're going to absorb almost 200,000 terawatts of energy just distributed, hitting every single continent, things like that. So really tons and tons of energy. To put this in context, that is 10,000 times the global energy use today. We all know that the sun is powerful. In California, we use it to grow nutrients inside plants and create harvests and fruits and vegetables, and weeds use them to grow aggressively. And no matter what we can do, we can't actually get rid of weeds because they're powered by the sun, which is incredibly powerful. So we have been trying as chemists to figure out how can we utilize the sun's energy for a long time, starting with Giacomo Cimochin, an Italian photochemist from the late 1800s. He was nominated for the Nobel Prize 9 different times, and he's thought to be the father of photochemistry. So he did the first photochemistry experiment in 1886. He pretty much exposed things to sunlight and was like, this is wild. There's going to be sometimes bubbling, gases evolving in situation. There's color changes. Anyone who's left a jacket they really like in their car over a hot summer has come back to find their jacket half a different color. This is because the sun, it sends you this light and it's going to interact with materials at a fundamental level. So Cimochin, he started the Department of Chemistry at the University of Bologna, and this is a picture of him on top of the roof of the university, just with a bunch of different flasks all sitting out, just seeing what chemistry is going to happen. It's a great picture. If you zoom in really far, he actually has 2 different buildings covered. Like, he's like, I don't need a lab space, guys. There's a roof, and I have these flasks. And up in the left is kind of an example of the type of reaction. So basically, you have a molecule, you expose it to sunlight, and suddenly the molecules connect together, almost like a polymerization. And more than that, he's also thought of as the father of the idea of green chemistry. So after the turn of the century, in around 1908 to 1912, he started writing these papers being like, the sun is amazing, guys. Why are we using fossil fuels? And in a seminal paper from 1912, published in Science and then presented at international conferences, he pretty much announced, we need to stop using fossil fuels. I have this great vision of the future. We don't need to keep burning coals and polluting our environment. We can convert to purely solar. He had a very fun idea. He didn't quite think of solar panels. Instead, he thought of giant glass tubes that kind of stretched out over Europe and all of the cities winding around, and all of them were full with some gas, absorbing light from the sun and essentially just netting that straight into the electrical grid. So we didn't quite come up with his vision, but we're still using the sun today to power a lot of different sources. There's 3 different ways we primarily harvest energy from the sun. There's going to be thermal energy, which it gets really hot outside. Sometimes asphalt gets so hot you can cook eggs on it. That's basically doing chemistry. So we have different ways we can harvest this energy. It's like contributes to heating of the Earth's surface, and we're all familiar with being warm. In the recent years, we started being able to harvest electrical energy from sunlight with solar panels. So in California alone, in a year, we generate around 20,000 milliwatts per year. That's around 15% of total California energy consumption. But that's not really what I'm talking about today. Many of you are probably familiar with those 2 areas. What instead I'm going to talk about is how can we use the sun to directly do chemical reactions, just like Cimochin was trying to do. So there's 2 different main routes we're going to go for. You're going to store energy in chemical bonds. Many of us are familiar with that, but how plants work. Plants are going to take sunlight and use it to power the mechanism of converting water and CO2 into glucose and oxygen, which we need to breathe. But glucose is very powerful, and they use it to power all of these cellular functions. The other option is that you use that energy immediately or directly to power a chemical reaction. An example we're all familiar with is color change sunglasses. All that is sunlight comes in and you're making a molecular bond break or twist or change in some way, and that's going to have a different interaction with light. So the way that we as a society think we're going to imitate what plants are doing is, instead of trying to make glucose and oxygen, which is a very complicated process using photosystem 2, a lot of great studies going on at SLAC about that, but is this idea of storing energy in chemical bonds. So specifically hydrogen gas. So that instead of putting gasoline into your car, you'll put condensed hydrogen and then use those chemical bonds to power your car. So comparing hydrogen to gas, it's going to 1 kilogram of hydrogen is about equivalent to 1 gallon of gasoline. A gallon of gas will get you 25 miles and will release a bunch of hydrocarbons into the atmosphere, whereas 1 kilogram of condensed hydrogen is going to be able to power your car 60 miles. And more importantly, when it combusts, hydrogen combusting with oxygen is going to have a main output of water, which is going to be much better to put into the environment than any sort of pollutant. So we're already working on a bunch of different ways to make hydrogen, mostly with electrolytic water splitting. You send in water, electricity, hopefully green electricity, and you're going to generate hydrogen and be able to release oxygen into the atmosphere. The photochemist's dream is to just take out the middleman. Why are we using this electricity that we had to generate and store and use batteries and put it into our grid? Why not make the sunlight do it directly? And that idea is essentially taking water, exposing it to sunlight and a catalyst, and generating hydrogen and oxygen. So the question, of course, for a chemist is, how are we going to design a catalyst that harvests sunlight and then takes those electrons that it's taking directly from the sunlight to do the specific chemistry needed to turn water into hydrogen? So that's going to be, again, breaking the bonds in water and then putting that energy and storing it into hydrogen. That then breaks, releases energy, and you can power a lot of things just like gasoline. So how can we make this catalyst be powered by sunlight? So a catalyst is, let's call it just a molecule that does some specific chemistry, like making hydrogen or really anything else. Chemistry can do a lot of stuff. The idea is that when you expose it to sunlight, you're taking a ground state and you're catalytically active. So instead of having to heat it up or electrocute it or expose it to energy, you ground state of some molecule. This is an example of a common photocatalyst, has a ruthenium surrounded by some other stuff. You expose it to light, it moves it up an energy level into this excited state, which essentially is taking an electron off of the ruthenium atom, the metal, and moving it onto one of these outer sphere ligands. And then that electron is accessible to do some kind of chemistry. And that's great, that's all well and good. There's a bunch of great research on this. There's actually a SLAC public lecture covering this topic from 2017 by Christian Kunis, talking about catching light is, I believe, the name of it, really talking about this process. So today I'm going to talk about what do you do when that's not the chemistry you want to do. That molecule can't do it. You instead want to use this. It's a platinum catalyst, really commonly used in a lot of industrial processes, but it has a different system. Instead of from the metal to the ligand, you want your ligand, so your chlorine's kind of around it, to give an electron to your metal. So you shine some light on it, and your light isn't quite enough. Doesn't work. Nothing happens. You don't reach this excited state. This is because light, as many of you know, comes in a spectrum. All different colors of light are coming down from the sun. The yellow line is what hits in sunlight on top of the atmosphere. Remember, to the left is going to be shorter wavelength, so higher energy, things like purple and X-rays eventually. And then to the right is going to be your infrared light going into microwaves and much longer wavelength and lower energy. From here, you can easily see the majority of sunlight hitting their surface is going to be of this visible band. That's actually why we see in the visible. It's the most important photons for our eyes to be able to see. And this is at the top of the atmosphere. You go through the atmosphere and all the different substances absorb these specific bands of light. So you reduce the yellow into that red line. So that's the radiation left over at sea level. So a little bit weaker, still clearly dominated by the visible region. And you can see notches in it that are going to be the specific absorption bands of water and CO2 and other things in our atmosphere. And the goal of this is that you want to design some kind of catalyst, a system that absorbs specifically in that visible region to harvest as much of this sunlight as possible. So for that system, you can actually separate it out and have a part that is going to absorb energy from the sun and turn it into an electron. And you have a part that's going to do the specific chemistry rather than having one system that does. You just connect them. You connect them using an electron bridge. And that's really going to be the theme of today. It's how do we make an electron effectively move from donor, the thing that is absorbing sunlight and creating an electron, to your electron acceptor, which is going to be the thing that does some kind of chemistry. This is an example of what the molecule looks like in real space. So going from one end to the other. However, you have a competing pathway. Once your electron leaves, your electron doesn't really want to stay left. It has all this energy. It got up in the morning and it was like, I'm going to go on a trip. But sometimes it goes there or goes out and it loses that energy. And so it's going to return home. And so our entire job as chemists is trying to make a unidirectional bridge where you have the electron go really fast and not turn around and come back. Kind of similar to, I'm sure someone in here has driven over one of these the wrong way. I know that's what that laughter was. So you want, they're called road spikes, where drive over one way, the other way they puncture your tires. We're trying to design molecular road spikes. So the electron moves one way, not the other. And you really want to do this because you want it to remain active as long as possible. This is going to be at least tens to hundreds of nanoseconds. That's how long it takes for this molecule to run into other molecules and actually do some chemistry. This is okay, though, because the electron moves fast enough, and we can do this. So here's a slightly less intimidating drawing of a molecule where you have the ruthenium portion, is going to generate an electron, and we're going to move across to the platinum. So upon photoexcitation, let's just kind of watch what the electron does. So you have an electron that's just hanging out in its atomic home inside the ruthenium. You electron moves the closest part of the bridge, and then a little bit of time passes, it moves to the center, a little bit of time passes, it moves to the spot, a little passes, and it finally arrives at the platinum, and we're ready to do some targeted chemistry. This entire distance is going to be around 2 nanometers. For comparison, the average width of human hair is around 50,000 nanometers. So this is an incredibly, incredibly small distance that this electron is moving. And the electron is moving incredibly fast. It's going to be much, much faster than a nanosecond, faster than a picosecond, even thousandth of a nanosecond, frequently on the orders of femtosecond, which is a thousandth of a nanosecond. Ugh. And then again, needs to stay there for 100 nanoseconds to do that chemistry, unidirectional. The problem, however, is sometimes your electron never arrives. Your collaborator spends months making these beautiful molecules, all of this theoretical design, it's going to work great. It doesn't do any chemistry. You look at it, and the electron never arrives. The question, has a troll consumed my electron? And if so, where? Has it been several trolls? How has it done this to me? This is really the job of a physical chemist, which is what I identify as. So there's many different kinds of chemistry. There's people who do calculations and design things. There's people who stand in a wet lab and do some amazing magic with flasks and glasses to synthesize these molecules. And then you have physical chemists who are kind of afraid of real chemicals, but are good at math and good at like using wrenches. And so we build these really insane 3-mile long instruments and convince everyone to use them, and we have a lot of fun. Really, our goal is to figure out what molecules are. We're figuring out how the molecule works, and more importantly, how it doesn't work. And then we work with our collaborators to tell them, this is exactly where this molecule went wrong. And so you can work together so they can do de novo design and fix this catalyst to, make a brighter future. So what do I mean by a troll? This can be the electron is stuck on the bridge. Your electron leaves home, gets to the bridge, and the bridge is really nice. Why does it want to go all the way to the platinum? The bridge is really nice. It feels safe, stable and safe there. It would be uphill in energy to go onto the platinum. Your option can also be that the bridge is too long and that there's a lot of traffic. So the electron, it's going really slow, and it would take longer to get away than it would to just turn around and go back home. That's where you have that competing back electron transfer problem, and where we want to invent this idea of like, no, don't go home. It's very hard to go home. And the last option that I'm going to talk about is maybe the electron just gives its energy to the solvent. It goes on the bridge, and then it meets like a really nice hobo, and it gives all its money to the hobo, and the hobo like swims away into the sunset. I don't know how that would go. Anyway, so really my job is identifying how has the electron been eaten or been sent back home because it's afraid of a troll. So how do you do that? How do you put cameras on an electron bridge? This is really tiny. This is only a few nanometers long. How are we going to put traffic cameras on a molecular bridge? The answer is lasers, because lasers are super fun. All right. So a quick rehash on lasers. Lasers are light waves, particle wave duality. They oscillate in waves. They're very targeted and collinear, so they can be powerful. Blue light is made of shorter waves than red light. Red light is longer waves, but particle wave duality, lasers are also particles. You're delivering literal units of light, energy. A piece of blue light has more energy than a piece of red light. Particle wave duality. They happen as both, and that's incredibly important for understanding how to manipulate lasers and use them to study things. We can thank this kind of concept to Planck, who around 1900 was like, hey, things can exist in quantum energy, photons probably exist. And then our favorite dude, Einstein, who literally every era of science, you just lead back to him somehow. In 1917, he pretty much trolled everyone and said, hey guys, I did some math. You can definitely make lasers. You can build up this light and deliver it in a coherent source so that you can shine a laser pointer, woo, laser pointer, and have it go really long distance without ever like losing, sorry, fumbled that. They go in a straight line for a really long time, which means you can point them at things. They aren't diffuse. And I say he trolled people because he said you could do this in 1917, and he clearly wrote out the math to do it. And then it took 45 years for someone to actually be able to physically make it. The first laser that was made is a ruby laser. And so imagine you have a brick of ruby. Literally, we use crystals all the time. Sapphire is one of the most commonly ones we use. So a laser is just any sort of gain medium coupled into an optical cavity. The gain medium, you shine light on it. In the ruby laser case, it was a flash lamp. And by shining light on it, you're giving a bunch of energy to this system. And everything's going to just start trying to get rid of that energy as a characteristic wavelength. You make it into a laser by putting mirrors on each end of the cavity, and only something that matches like a multiple of that cavity is going to oscillate. This is why they are actually able to make a maser first. So that is a microwave laser, because you can imagine that making a cavity that's multiple units of centimeters is much easier than one that's multiple units of nanometers. And so just aligning and creating it was really hard. Then there was the wild west of laser inventions. In the 1960s, there was so much going on, and there actually was like a 30-year litigation on who really deserved the Nobel Prize and who actually gets the patent for making lasers. Really cool stuff, invented a bunch of things. Then came Donna Strickland, who in 1985, she came up with something called chirp pulse amplification, which is essentially a way to make a very high power pulse laser. And that enabled using these to study chemical methods. So Donna Strickland got the 2018 Nobel Prize for this method, and then the 1999 Nobel Prize went to this man named Ahmed Zewail, who is essentially the father of femtochemistry. He's the one who took these lasers and used them to solve chemical problems. The way you did this is that these laser pointers that everyone's mostly familiar with, these are called continuous wave lasers. So they are constantly emitting in time. However, by doing some interesting optical cavity stuff, you can have the lasers deliver instead tiny photons at once. And these pulses can be incredibly short. And I'm talking microsecond and nanosecond, followed in the 90s by picosecond lasers that you can control well. And then after that, femtosecond lasers. So a femtosecond is a millionth of a billionth of a second. That's very, very short. And if you have a femtosecond laser, it's like a camera. So you have a camera that has a very fast flash speed. So at a public lecture a few months ago, someone used the example of a hummingbird. With a really slow camera, so a long exposure time, you can't see the hummingbird's wings. But if you make your exposure time shorter and shorter and shorter, you can start resolving and seeing those hummingbird wings. And that's why femtoseconds are really important for studying chemistry, because that is the rate at which electrons move along a bridge. Attoseconds, even shorter than that, very great. A lot of cool talks on that for interesting physics things. And then y'all can go and watch their lectures if you want to hear about them, because I'm really only talking femtosecond. So talking explicitly how you do this is what Zewail did is he was like, okay, one laser, and what if we use two? It's a technique called pump probe spectroscopy. You use two lasers. The first one delivers a pump pulse. That is going to be a piece of visible light. It's going to imitate the sun. You give it to a molecule and it goes into the excited state. What happens to it if it gets exposed to light? And then you come in with a probe pulse. And that again, that's your camera. You're taking a picture. And by changing not the exposure time, but when you take the picture, it's like if you take a picture 1 second, 2 seconds, 3 seconds, things like that. And the great things about lasers is they're collimated. And all light travels at the same speed in a vacuum. So by literally changing the distance that you are having on your alignment path, you change the arrival time between the two, and you're taking photos throughout time. And you can really remap the electron movement process. Zewail's work, all the light was visible. And we're at SLAC National Lab. Why am I talking about all this optical stuff? So energy describes the color of the light. So visible light, we're now talking in EV, is a unit of energy. Visible light is going to be very short. It's going to be like 1 or 2 EV. X-rays are much, much bigger. They're going to be 1,000 EV or 100,000 EV. The reason that this matters is because this is going to be characteristic on an element by element basis. So we use SLAC because SLAC is an X-ray laser. We can use tabletop things to make optical pulses of light, but you really need these massive facilities to make incredibly short pulses of X-ray light because they move completely different from other light. And the source needs to be really long because you want it to be really intense. The more intense your pulse, the better your resolution of your camera. So it's really short. Why do we use X-rays? Here, you have a nucleus, you have a bunch of electrons sitting around. Your X-ray light comes in and it kicks out one of the electrons in an inner shell and it moves it into the valence level by absorbing that piece of light. So if you have nitrogen, it's a very small distance, just a little hop for that electron from its home to the valence shell. If you have a bigger atom, like a metal, like this ruthenium, you have a lot more layers of electrons, and it's going to be a bigger distance that it has to go. Same thing for platinum, even bigger than ruthenium, so your electron has further to travel to get to the valence band or to where it wants to go. So a little bit of audience participation. How much gas does it take to go from the surface? I'll give you an example. Nitrogen is 400 eV. Who is brave and wants to guess what it is for ruthenium? There's no kids today. Adults are not brave. 1600, that is a good guess. So this is a huge difference. And that is not because it is just a distance change between these atoms. As you get bigger and bigger, the core of these atoms is pulling its electrons even stronger. And so the electrons are having to fight incredibly hard to get out of the center of the atom. Platinum, I won't ask anyone to guess because I know everyone's feeling very nervous tonight, is 72,000 eV. So again, platinum, not that much bigger than ruthenium, but pulling those electrons even harder. So it becomes very hard to escape. But the great thing about these being different energies is they're characteristic. If you shoot a bunch of different colored X-rays at things, you can tell exactly what elements are there just by the energy that they absorb. So that's why we have free electron lasers and synchrotrons. On red there, those are the energies that you're able to, those are the energies you need to identify if that element is present. And different beamlines and different facilities all across the globe all have different energies of X-rays that you do. So the way you actually use the instrument is you write these proposals, you mail it off, and they say, we'll give you 7 days in 2 years. Prepare really well because that's the only shot you have. Can be very alarming, but it's really amazing the information that you can get from these facilities. So what this looks like in practice is you have your X-ray light and it goes in and it hits a sample. This is it as a powder. The X-ray either transmits through the sample or you measure it some other way, and you really just see X-rays before you hit the sample and X-rays after you hit the sample, and you just subtract those. And so if you have a ruthenium, you expose it and you see this peak. Remember, this is my camera. This is the X-ray camera. I'm taking a photo of it. This is what my ruthenium looks like before it has a piece of light, so before it loses an electron. So you photo excite it with your visible light pulse emulating the sun. Nice lightning bolt on the ruthenium. And you can answer this question of, has light created an electron? And you're going to answer that by if this peak moves left or right. That peak is going to change, and if it changes, you can say, hey, the electron has left home. Lets you know, no troll at the ruthenium center. You can then go to a different beamline with a different amount of energy, and you can look at the platinum. Same exact thing. You shine light on it, start the electron leaving the ruthenium, and if you see a change, you can answer the question, has the electron arrived on the catalyst? Just by the movement in this peak of this energy. And again, we're taking these X-ray photos incredibly fast using these lasers, so your distance and time can be femto or picoseconds. So again, every millionth of a billionth of a second, you can take a picture, take a picture, take a picture. And so you can not only see, has something arrived there, how long did it take to arrive there? Lastly, I'm going to talk about nitrogen. So nitrogen, you can see much lower energy, but there's a lot more nitrogens throughout this molecule. So if you shine light on it, start an electron moving, you can identify exactly where on the molecule is the electron just by looking at one of the nitrogen. So if it's still around the ruthenium, you're going to get a change in this yellowish peak. If it's gone to the center of the bridge, you're going to get a change on the greenish peak in the center. If it is on the platinum, the catalyst part of your bridge, you're going to see a change in the highest energy peak, that blue one. And this can be incredibly diagnostic because now you're able to map the entire molecule and with using one energy, and you're crucially able to look at the bridge step. So why? I mean, you might have noticed that the ruthenium had one peak and the platinum had one peak, but the nitrogen has 3 peaks. This is because there's different chemical signatures. You're measuring that in of the nitrogen. So this is the where you're moving an electron from the most core of the nitrogen to the surface. But this is a nitrogen atom. It's just sitting in gas, not interacting with anything. When you put it into a molecule, it has a bunch of other atoms around it. Those other atoms are going to fill the valence shell, so they're going to share some electrons. And the center of the nitrogen, all the other electrons are going to respond to the presence of the new ones. They're going to pull in closer to the nucleus. So kind of reacting back and forth, what is around it? And that's going to, what's around it is going to change. So the valence, the core is much closer. The valence shell is full, so it's having to go even further to escape this electron. And just like we showed earlier, if the electron has further to go and it's a harder job, you have to use more gas to get there. And that's going to move your peak. And that's going to be diagnostic of what the nitrogen is bound to. So in this way, we can start answering this question of what part of the bridge is the electron getting stuck at? If it's in the center of the bridge, you're going to see a change on the yellow and green peak. If it gets stuck on the ruthenium part of the bridge, you'll only see a change in the yellow peak. If it gets all the way to the platinum part of the bridge and you see a change in every single peak, you can then use that as traffic cameras and not speed map, doesn't word, the speed, how long it took to get somewhere. And that's incredibly powerful. So, thought I already did that. So let me talk a little bit about the actual experiment we're doing. So this is a brand new instation at LCLS. So some of you might or might not know, LCLS is undergoing an upgrade right now. We're becoming LCLS 2. And what that means is we're supercooling an entire portion of the accelerator. And by supercooling it, we can make our electrons multiply even more. So the source is going to be 1,000,000 times brighter. And once again, you can imagine what that's going to do to your signal to noise. If you have a really bright light, you can see better than a dim one. Like if you get a splinter, you don't sit in your living room. You go into the bathroom under the brightest light you have to see as well as you possibly can. So this is going to really improve our signal to noise. And so we built this new in-station called KIMRIX. So this has a comedically complex sample delivery. I say comedically because you want to deliver these molecules to an X-ray beam, but you don't want them to be a powder. Chemistry doesn't happen in solid state. It happens in solution, interacting with the solvent in the environment. You're mixing a bunch of things together. However, nitrogen absorbs at 400 eV. I mentioned that a few times, and that's because that's significant. As soon as you go below around 1,000 eV of light energy, you have these photons, they're getting pretty weak, and they're just going to start interacting with everything, including the atmosphere, air, any solvent you put it in, any optics. So you have to do the entire experiment under a vacuum chamber. So this has to get to around 10 to the minus 5 torr. That's, space is something like 10 to the minus 12 to 10 to the minus 17. So not quite at space level, but it's not very much air in there. You have to use a couple of different vacuum pumps to get it out there. All right, so do the entire experiment vacuum chamber. People do that. But remember, I said this is a liquid that I'm putting in. So I'm shooting a liquid into a vacuum chamber, and it interacts with air, so it's definitely going to interact with any sort of cell that I put this liquid in. So I'm going to just shoot bare liquid. I'm just going to jet liquid into a vacuum chamber, an exposed nozzle. And, one of the ways we do this is you sit a nice round jet. People know how to make round jets. That's very reasonable and very nice. But For X-ray absorption, you want a nice homogeneous surface. So you want a really flat jet. So you want an ultra thin jet. And by ultra thin, I mean, a few micron thick. So we designed this insane microfluidic chip design. So instead of jetting a round jet of water, you have this micro chip and it has different channels. And as the channels come in, they shoot liquid out, the liquid hits into each other and splashes out in this leaf form, and then splashes out into a leaf form, and then splashes out into a leaf form. And you can engineer these so delicately that you get something that's maybe a millimeter wide and then only a micron thick. So over on the left is one of the first examples of this. You had this kind of colliding chip, and you can see there was still a lot of interference. It wasn't perfectly smooth. I show that picture to show this converging nozzle. Look how amazingly smooth that is. You know that's smooth because you see those bands of light. We actually use those bands of light to figure out how thick this sample is. And by the bands of light interacting, you can figure out how thick it is. So again, very thick. This jet that this is a photo of is around 5 microns thick. Once again, compared to human hair, that's 20 to 180 micron thick. So this is significantly thinner than even the finest baby hair. And it's a millimeter wide, and we're shooting it into an exposed vacuum. It's pretty insane. And we have one more problem. This isn't reasonable at all because these samples are precious. They're so precious that just a few grams of it is going to take a collaborator 6 months to 2 years to synthesize. You do not make friends if you're like, hey, I want to do an experiment. Can I have like 3 years of your life making this one sample, please? And, so we're like, okay, we really want to do these measurements. Really precious samples, you're going to synthesize those in like tens of milligram amounts, very, very small. And so you really want to ask someone for under a gram. And so in order to do this, we're like, great, we're already shooting an insane liquid jet into a vacuum chamber. Let's also add this catcher. So this is a heated copper tube, and it's like attached to its own vacuum chamber. So you shoot a liquid jet exposed into a vacuum, catch the water, suck it out, and recirculate the entire thing. And so we only recirculate around 50 milliliters of it. That's significantly less than I have in this glass. And this is just, it's so much engineering went into this. I put the publication on there. I know you're all going to rush out and read it. It's very impressive because now instead of asking for 16 or 20 grams of a sample, you can reduce that and ask for 500 milligrams, which makes you lots of friends and has people actually want to do an experiment with you. I went over this just because I think this is one of the coolest things about science is the truly comedic things you do to make an experiment work. Again, 50 milliliters for around 8 hours, constantly being exposed to things. So we did this experiment last year, and we just did the first half of this bridge because this was a brand new instation. And again, it was actually designed for LCLS2 when we have a million times better source, but we went ahead and had to test it before we had that because, of course, just like do your experiment with a million times less photons, that's fine. So we did this experiment, and we were able to show that the electron does, after being excited by light, land on the bridge. However, from preliminary results, we're finding that there's also a troll there. The electron never wants to leave that bridge. It's too stable, it's too happy. There's like a cafe on the bridge and all kinds of other stuff. It never actually wants to go all the way to platinum. Who wants to drive that far? But the really important conclusion from this isn't that we found one molecule that didn't work, it's that we found a mechanism for why it didn't work, and we built this system that's modular. So the reason I have these drawn in separate parts is because the entire ethos of this project is to build these like building block linkers. So imagine these are Lego sets where you have a bunch of different electron acceptors and one catalyst. You pick the electron acceptor that absorbs the color of light that you currently have. Or you have an electron acceptor, so thing that turns sunlight into electrons, and it's incredibly good at absorbing blue sunlight, which hits your office at the perfect angle each day to be very intense. And so you can just swap out the electron acceptor, the catalyst, and do whatever chemistry you want using this linker you've already designed. So the example here, if your bridge doesn't work like the ones we've used, we can just substitute out a new bridge. And again, that still has nitrogens in it. So this technique I described is still going to be useful for figuring out if this system works. So we've been presenting this at conferences and scientific meetups recently. Every single person you talk to is really excited about the ability to look at nitrogens. This is because nitrogens are ubiquitous in these types of systems. Here's a bunch of bridges. You can notice that there's nitrogens everywhere. Nitrogen, it's like carbon. It's one of the building blocks of all chemistry, and it's incredibly important for understanding these systems. So many people have come up to us and are really excited about, when are you going to get the good enough signal noise that you can move into harder solvents, that you can move into this? It's been really fun to talk to people about all of the different experiments that you can do going forward. And this is here at SLAC National Lab. They've been building it the last few years. It's going to be really great. So in conclusion, kind of what I've talked about to you today is how you use ultra short X-rays to track this electron movement in these kind of bridge system, in these light harvesting systems that are modular. And this has a bunch of great applications. It's going to be really cool going forward. So that is searching for trolls under the electron bridge. Also, always a plug for collaboration. Science is a team. SLAC is a massive facility. These are like 20 different people who all work together just to do that one experiment, and many, many more. Again, Christian Kunis, Catching Light, a previous SLAC public lecture, really great introduction to the chromophore, so the light absorbing, turning it into an electron. Really great introduction on that. Highly recommend. That's all.
Right. So, Liz, thank you very much. I guess there are some members of this team in the audience too. You want to raise your hand?
Yeah, team members over there.
Very good. So we have some time for questions. So here's the deal with the questions. This lecture is being recorded, and it'll appear, I guess, in about a week on YouTube, on our SLAC YouTube channel. If you'd like your question to be actually in the recording, which I hope you do, please wait for the microphone to come to you and then talk into the microphone, and then Liz will answer the question. So please raise your hand to ask a question and I'll recognize you. Sir.
Hi, thanks for the talk. I wanted to understand with the absorption lines, like what does that mean? Like a certain electron energy is being absorbed and then you don't see it at the end or something, or?
Do you mean like from the solar spectrum?
No, there was like the plots that you were showing to work out where the electron had gone in that system.
Yeah.
Like this?
Yeah, those ones. Yep.
Okay, sorry, can you repeat your question just so
Sure, yeah. So what does that like peak mean? Does that mean those electrons never reach the end, or?
No, this is the initial spectrum. So this is at the ground state. So before you ever photoexcite it, you're sending in this color of X-ray light. And it's going to absorb based on just the identity of the atom. So an atom, it exists at the center with the nucleus. It's going to be positively charged, and then you have electrons existing in layers out of it. X-ray is called a core level technique. All X-rays are going to take one of the innermost electrons, give it energy, and leave. And so that is the energy it takes for an electron to leave the center of the atom. And that energy, the amount of gas it takes and the distance it has to go, that's going to change by everything that's around it. So this is just a ground state measurement. And then if you photoexcite it first, these peaks are going to move, and you can identify what part of the bridge it's on by which peak moves.
Oh, but let's be a little, could you go back to the ruthenium, the original peak that you showed?
Yeah.
There we go. So the question is, why is there a peak rather than a spread?
Yeah.
And the answer, yeah. And
so it's a bound transition versus ionization. So ionization means the electron just leaves, gets skyrocketed, never sees home again. A bound transition means it's moving in between orbitals. So it could be in between the closest shell and the one like third up, or the closest shell and the valence. And so it's a bound transition because it moves a specific amount. And then I don't show it here, but each of these, it has this pre-peak, and then there's kind of this big step function. that happens after it.
And in atoms, these levels are very discrete. They're definite energies. So it's a very narrow band of X-rays that has this large probability to go from exactly this shell to exactly that shell. And that's used in all of these techniques and many other, and the rest of chemistry too, I should say.
And so platinum is a good example because you see that sharp peak and then you can already see the ledge, and that's the ionization energy. So it's a big shelf kind of with a main peak. Thank you. Thanks for the question.
Who else? Sir.
So I'm thinking about the exclusion principle and the fact that you can only have one electron with one quantum number in one spot. As these things move along the chain, is it actually one electron going each step? Or is one pushing on the end of the whole end of the chain and pushing another one out the other end? Can this technique actually just answer that question?
So the technique, I think, can't actually answer that question because it's going to be a resolution issue. And I think depending on the different system, it's either going to be the same electron, because the electron, it's moving in something called the LUMO, the lowest unoccupied orbital, because electrons, path of least resistance. So it's hopping into the lowest space. And so the same electron is moving because usually it's that one, the idea is that the one electron has all this energy. And so it's hopping, it's starting out, it has been sent a bunch of energy, and then you design it so that the bridge is lower, is an easier path for the electron than otherwise. So it's usually the same electron that is just kind of bouncing around trying to find its lowest energy place. But I think like if you go into solid state materials, they tend to think of it as like, a phononic mode of electrons bouncing against each other and things like that.
What made you decide to become a scientist?
Ooh. I've always liked science and a lot of stuff. It's really fun, but I had an internship as an engineer after my first year of college, and I hated it so much. I changed my major. I worked in a plant all summer, and I just, felt like I was selling happiness. So like selling my soul. Selling happiness for money. I don't know how to phrase that. And so I changed into a chemistry major. And then at the end of college, I just really thought science was interesting. Thought I'd go see what grad school was about. Thought it was fun.
Can you help me understand how you capture the data on the back end of these things when you have femtosecond resolution? Like, what does the data capture look that's coming out of this process?
So the data capture, so it's femtosecond resolution, but you measure the same step many, many times. And so the detectors only need to run out at like, per second or something like this, or per microsecond, something much, much slower than that. And so there's kind of three main ways that you detect this. This is a good slide to be on for that. So you can either have transition mode, which is what I have documented here. You just measure before and you put literally a CCD camera, like a literal regular camera that can detect afterwards, or just a photodiode that's counting the number of the photons that are hitting it. So that's one way. The measurement that I actually have here is something called total electron yield mode. And so this is, you grind up your sample into a powder and put it onto conductive tape. It's carbon tape that's sticky, and you stick that onto a piece of copper, something very conductive. And then you literally just pretty much attach a voltmeter, and through the photoelectric effect, a photon hits this, you create this electron, and you measure the drain current that's just bleeding out of it. And that's called total electron yield mode. So that's two different ways we can measure this. The third way is fluorescence. So when you shine a piece of light on it and generate this electron, that electron eventually loses its energy. And if it loses it back to where it was, it'll emit a characteristic photon, and then you can put a photodiode in front of it. And so that's for when you have like a really cloudy sample or a solid or something like this. So the main three ways to detect it. But luckily, sample readout isn't a problem, but that confused me so much when I started grad school, because I was like, femtoseconds and what? Like our camera is reading out at half a second. So yeah, it's that you do the same measurement many, many times, and then just by separating the distance the laser goes, that gives you the femtosecond resolution.
Thank you.
Can I expand on that question?
Yeah, please do.
How do you know how long it is between when the two laser pulses hit?
So that is a really fun thing. So you essentially measure something called time zero. And so it's a little bit harder in the X-ray, but if you have two optical lasers, you send one through a non-linear material. So you send a laser going this way, you overlap another laser going this way, and then you change the distance, like a delay stage, just add a leg or something like that. And through this material, you actually will have it add photons together, and it'll change the momentum, which is the angle. So you have a crystal, one laser goes this way, one laser goes this way, and when you have time zero, when they arrive at the same time, a third laser comes out at an angle in between those, and you stick a white piece of paper behind your crystal, and you stare at it and stare at it and stare at it until you see a blue blip, and then you yell at your lab mate, go back, go back, go back, and then you realign it, and you just kind of manually move those. So that calls time zero. And then again, all light travels at about the same speed, and especially the same speed in a vacuum. So literally by changing the distance of the path of the laser, you're changing the amount of time it takes to get there. We can literally have tape measures that will have like millimeters on one side and picoseconds on the other side, and you can measure the distance because electron or light moves at the same speed. It's very fun. It's very pretty.
Please, you have the next question. The microphone's.
I have two questions. So the first is, why do you only push the electron from the innermost to the valence shell and not just directly out of the atom?
So it's the type of measurement I'm doing. There's actually both kinds. So you can have scattering. So, okay, this is an absorption measurement. So we are literally looking for that transition. So we're scanning across all these energies and seeing where it is because we're trying to identify the energy of that valence band. That's one of the things we're looking for. So if you have a measurement where it kicks it out, that's going to be a lot of the scattering techniques, which isn't what I do. But basically, they kick out that electron and then they track that electron hitting other atoms and bouncing around, and they see the energy of the electron after it's hit a bunch of things. So that is also an incredibly important technique.
And then the second is, I know you showed a lot of the bridges were like nitrogen based because it's relatively versatile like carbon. Is there any other element that could achieve the same effect or that you've experimented with?
So I haven't looked at a lot of other bridges just because we're working on this nitrogen technique. But yes, it's a huge field. You actually have people who are even using like carbon nanotubes or something like that, or yeah, lots of different kinds of bridges. Couple of the ones I show actually have like zinc and carbons and stuff like that. So there's so many different kinds of bridges, and it's a huge field of research. Let's see, fluorine and sulfur shows up a lot. Thank you.
Way in the back.
What if you switch to heavy hydrogen deuterium? Would you expect any new phenomena from that?
I don't think I know what a heavy hydrogen material is.
Sure.
Oh, deuterium. Yes, you would expect a change from that. So if you do deuterium instead of water, you're going to, again, be changing the electron orbitals. I don't think I have a more specific answer than that.
Yeah, it's deuterium in the hydrogen generation process. You want to generate D2 instead of H2. It's just there's a lot more hydrogen. So
yeah, there's a lot more hydrogen. So deuterium and heavy atoms are really important actually for this entire field of research. And that is because this is chemistry. So if it's hydrogen evolution, you can deuterate your solvent, the other parts of the catalyst, and you can actually use that to find out where did the hydrogen that I'm using to do this reaction, where did it come from? Am I harvesting hydrogen from the solvent? Is it from like an electron donor? Is it being ripped off of the like glass container I'm making the experiment in? You can deuterate various things and really track those to see what is contributing the important part to the chemistry.
But for cars, we just don't, it's expensive to collect enough deuterium to power a car.
Yeah.
So you better do it with ordinary hydrogen.
Yeah. Plus,
Okay.
SLAC deuterium's a big no-no substance.
Oh, okay.
You get a bunch of really mean emails if they think you've lost a bottle of deuterium. It's very confusing, especially if you haven't lost a bottle of deuterium and you don't know what they're talking about.
Okay. Let's take two more questions. Who has them? Please.
So you mentioned LCLS2, is that the right? And I think there are 2 orders of magnitude higher fidelity measurements that comes with that. What does that mean for your experiments? What are you going to be able to see?
That's going to be amazing for these experiments because the sample right now, we have to do it in water. The reason you have to do this delivery in water to look at nitrogen is because carbon absorbs at 250 eV. And like that gentleman asked about, there is a shelf. You're going to ionize all of your solvents. So it's going to make massive background. And so if you have a carbon solvent, there's currently too big a background for you to be able to see your sample. Once you have this huge order of magnitude improvement in your signal to noise, you're going to be able to expand this experiment to different solvents, which is what it was designed for. And you're going to be able to still have great signal to noise in that. And you're also, of course, going to be able to reduce the sample ask. We did this experiment at 100 millimolar, which means that it's basically sludge. And jetting sludge is like a huge problem. I broke several pumps and probably made enemies. So yeah, it's going to be really amazing. So the in-station was designed for the upgrade. So it started receiving that light in maybe November. And so they're really excited. I think the first experiment is this February with the upgraded light source. So it's going to be really cool.
We're saying a little about this. It's not that the light is going to be a million times brighter. It's that you're going to have a million times more pulses per second of about the same size. So the way that's achieved is by using a different kind of accelerator than they're using now at SLAC. The old SLAC is based on a 1960s, basically, version copper accelerator. They've just cleared out a third of the tunnel at SLAC and put in an accelerator based on superconductivity. So you can bring that down to a degree or two above absolute zero. And then this material is it maintains high fields and you don't lose power and you can shoot it much more often. And the idea is to shoot at 1 million pulses a second instead of 120 pulses a second for the ordinary SLAC. And so each pulse can give you data. And so it's just going to be much more powerful.
It's going to be amazing. We're going to go from collecting something like a terabyte of data every few minutes to a terabyte of data per second. And yeah, yeah, I think there's a lot of concerns about how are we even going to store that data? And then I think we don't know how to do it right now. And so like one example is there's someone working on machine learning to look at all the pulses in real time and just be like, never mind, that's not real. Don't even store that. That's not real data.
Well, you know what? I'm a particle physicist and we deal with this at the LHC already. So
yeah.
In principle, we know how to do it. And it's just bringing those techniques to this field, which we hope is ready for it.
Another really cool thing about the upgrade that I'm excited about is X-ray sources like this, these X-cells, the X-ray free electron lasers, there's 6 of them in the world. They have this problem that's called jitter. And that's because this source is so stochastic that your X-ray, it might not arrive exactly where you clock time 0. It's going to be time 0 plus or minus a picosecond. And that picosecond can be very frustrating if you're looking for like a 1 picosecond dynamic. So you actually have to have a separate entire experiment that has to happen during yours where you just clock when did the X-ray arrive, and then you have to do a bunch of complicated math to like resort all of your data. And something about super cooling the accelerator, which I actually don't understand, I keep asking people, is something about this, it's going to have significantly less jitter, something on the order of 20 femtoseconds rather than 900 femtoseconds. And so that's going to simplify data processing and simplify data collection for in time. Because again, these are kind of high stress experiments where it's like 5 a.m. and you have a 12-hour shift and you're just like, make this choice, make this choice. Do we move the time or not? So I'm really excited about that. It sounds cool.
Okay. Anyone want to ask the last question? please.
I may have missed this, but I was wondering, how do you actually build the bridge? Is it just a solvent and you spray the lasers through them, or can you explain that a bit more?
How do you build the bridge? So that's going to be a synthetic chemist. And so these bridges, so I have the molecule up here now. So you basically take parts of the bridge and then you sometimes expose them to light and it causes bonds to form. I'm not a synthetic chemist. I don't know how to explain this well. Really impressive people mix things together in weird temperatures with weird gases. And great final question.
Right. In your organic chemistry course in college, you get much simpler problems like that, assembling different bonds to get what you want. But the complicated ones, it's just black magic.
Yeah,
And
it's
people-
real impressive.
people have gotten the Nobel Prize for introducing new kinds of black magic that enable you to do previously
Yeah.
inaccessible syntheses.
Mhm.
And so now we're profiting from all of that to actually get these bridges in the first place.
Yeah. And that's actually one of the coolest things about these donor bridge acceptor applications is for this, the area of photochemistry. So literally using light as a reagent in your chemical reaction is a booming field right now. In the last 10 years, there's started to be lots of publications on it and pharmaceutical companies actually doing photochemistry as like inline industrial processes. Basically, light can be a very targeted reagent. So it can do something like helping you with the handedness of a molecule. So handedness is called chirality in chemistry. And so that's going to be take an orange and a lemon, the thing you're smelling, literally the same molecule, just different handedness. They're mirror reflections of each other. And another example of that is a lot of medicines are amazing. And if you have the wrong handedness that turns the wrong way, that's actually going to be a poison. There's something called the thalidomide scandal, where in France in the 70s, maybe the 80s, a bunch of pregnant women, 60s. Great. So, okay, y'all know about the thalidomide scandal. For those of you who don't, basically, one-handedness of the molecule is a treatment for morning sickness. And so a lot of French women were given this to treat morning sickness, and it caused the other handedness of the molecule causes extreme birth defects. And so there's a generation of thalidomide babies who are born with these extreme birth defects. And plug for women scientists, it was in France and it was approved throughout Europe, but the FDA, it was not approved for use in America, which is why a lot of Americans don't know about it. And it was a single woman at the FDA who had a chemistry background and was like, the research on this is not good. We should not be giving this to pregnant women. And she had a lot of political pressure from her boss and bosses being like, no, just pass it. It's fine. Everyone else said it's fine. And so just an example of one person thinking something through carefully can really change. And yeah, got to be very conscientious and careful in science. But point of that story was that light can be a very targeted reagent. And so it can help you synthesize just one-handedness of a molecule rather than the others, just because those are going to be at slightly different energies. And so maybe synthesizing at 455 nanometer versus 465 nanometer light, which is both blue, but it'll have a slight difference in the outcome of that reaction.
Thank you.
Well, let's thank Liz again. This has been very exciting. Okay. I apologize that this auditorium is going to go out of commission during March. So we will not have the traditional March public lecture, but we will have one at the end of May. It'll be pretty fascinating. And every 2 months, we'll bring up another one of these. If you want to get on our mailing list, go to the SLAC website, look for public lectures, and there'll be a way to get on the mailing list for these events. And we hope to see you in May and in the future. So thanks to you all for coming, and I hope you've had a good time.